All right. So, great, thanks. Yeah, it's time, so let's get started. Hi, I'm Allen Rohner, and this is Breaking the Bank with Contract Testing. So I am co-founder and CTO of a bank written in Clojure. Sorry, no, not that one. That's New Bank out of Brazil. Sorry, no, not that one. That's Crew Bank out of the UK. This one, Griffin Bank. So we are a fully authorized UK bank as of February 29th this year. The entire system is built in Clojure, including the core banking system. We are an API-first B2B bank. Our customers are almost entirely fintechs, and we built our own core banking system. So now I have opinions about testing and quality, and you guys are going to hear about them. The source tree is called Banksy. It's about 7 years old. We have 150,000 lines of source and another 175 of source, 150 of tests. And so today we're going to talk about how and why to write good deterministic system tests and how to use test.contract, which is a library that I open sourced, and what lessons we can use on that from these kind of deterministic system tests to build good systems that are testable. So let's talk about some definitions. The pure functional programming community typically treats side effects and nondeterminism as kind of the same thing, and they kind of lump them all together as impurity. But in the context of testing, we care about the difference between them, and so I'm going to distinguish between them today. So side effects are if you have a function call and you can't just replace the call with the return value because something else is going on, that's a side effect. And that typical examples of that are reading and writing to disk, sending network messages, mutating atoms, like actually mutating any non-local variable. And then on the other side, we have nondeterminism, which is when if you have a function call, you can't predict the return value from the inputs alone. So that's things like random int, random UUID, getting the system time. Now, the reason we have to treat these differently and the reason we care about both of them is that to get good tests, you have to get rid of both of them. And you have to do that in different ways. So we want to get rid of side effects in our tests because, well, I mean, one, they're just slow, but two, they're fallible, right? So this is one of the main sources of test flakes, is that if you're testing against a third-party API, like the network could be down, any number of things can just break, and that'll cause your test to fail. And then nondeterminism you want to get rid of, partly because we're using quick check, and then partly because you need reproducibility to have confidence that if you see a problem and then you fix it, it's now gone. And why do we care about testing at all? The ultimate goal is to get confidence that we've released good code to our users, right? There are many ways to do that. Like you can start with a good program design. You can use a better language. You can do code review. You can look at code coverage metrics. You can use formal methods. But hot take, there are no correct programs that have not been tested. But there are correct programs, written using bad languages. There are correct programs that never went through code review. So basically, everybody who wants to end up at a correct program must test, but all of the other techniques are more optional. I'm just going to take it for granted that you know what quick check and test.check are. If you don't, pause the recording, come back. There are dozens of hours on YouTube. Go watch some of those talks, and then come back. But the things we care about today are quick check, because you separate the input generation from verifying properties, you can generate an infinite number of test cases, and then you can run as many of those as you feel like. And that means you get to trade off test speed for coverage, which is really powerful. And then the second thing is because the other requirement is that because we have shrinking, so like you generate a sequence of calls, and then you find something that where your property doesn't hold, and then quick check tries to shrink the inputs, you're rerunning the test. And when you're rerunning the test, that means you better not have flakes, because otherwise that'll screw up the algorithm and you won't be able to shrink properly. So reproducibility in your tests requires determinism, which means try to avoid or eliminate random int and system time and all of that. So let's talk about the Platonic ideals of a test. Like what in the perfect state, what does that look like? I mean, the first requirement is just it finds bugs, right? If you're not finding bugs, what are we even doing here? The second is that you need good test coverage. So it's not enough to say, oh, I've tested this function or this namespace or even this module really well, but then I haven't tested this other thing, right? Because if you deploy that to production and you break, like it's still broken. That you've eliminated half of the bugs is not good enough. You need coverage over the entire system. The third thing is that you want efficiency. And this is mostly about like the effort spent writing tests and debugging to the ratio of how many bugs you find. All things being equal, it's better to spend 1 hour finding a bug rather than 100 hours of debugging and looking at logs and all of that. So tools that let you find bugs with less developer time are more powerful. You need your tests to be fast. Partly this is laziness, like just impatience of just, I don't want to sit there and wait. But you get a lot of productivity advantages from this. So of course, a 1 hour CI time is better than 4 hours. But because we're using quick check, that means that the faster your test, a single cycle runs, the more cycles you can get in the same amount of time. So this is, again, allowing you to trade off speed for coverage. And so the faster you go, the more coverage you can get on your system in the same amount of time. And then finally, determinism. Again, I'm going to keep hitting determinism because this is one of the main places where people fail. So we're using quick check. We need our test to be reproducible. But the other thing is flakes are just a complete productivity killer, right? If you have a 1 hour test suite and 10% flake rate, that means that you have a 9% chance of your test suite taking 2 hours and a 0.9% chance of it taking 3 hours, and on and on. So one that totally kills productivity, like how many people here have deployed, tests failed, and you say, oh, maybe I should hit retry, and that'll fix it, right? And then you get to like 3 or 4 times, and you're like, okay, there's actually a bug here that I need to stop and figure out and fix, right? Has anyone done that? I do it all the time. But even more insidious than that is that you need to know that when you've seen a bug, that you fixed it. So the other thing you see is like, okay, the code's running in production, and then it blows up. And then I don't know what happened. I've got logs, and I can stare at it and debug it. And then I write some code, and I write some new tests, and then I deploy it, and CI is green. Did I fix the bug? You don't know. And you can't know unless your system is deterministic. So in the ideal state here, when you're running your test suite, there is zero non-determinism aside from your quick check seed, right? Because then you say, that is the only source of non-determinism, and then when I find an input that causes the error, then I can fix the code and then run that same seed again, and if I don't see it, then I know that the bug is fixed. And anything else, you're guessing. So there's a lot of traditional advice here about how you should structure your test suite, right? So on the left, we have the test pyramid, which kind of looks like the food pyramid and is about as accurate, right? They say, oh, you should have 70% unit tests and 30% integration tests. And then on the right, we have the end-to-end camp, where they say, oh, you should set up an exact replica of production and then test it using only the methods that your users will actually use. And so, browser tests. And this is how you end up with like 4 hours of Cucumber, right? So, but they both kind of have merits though. Like the test pyramid people are right, and they say you should use mostly unit tests because they're small and deterministic and fast. And the end-to-end people are kind of right that if you don't do end-to-end tests, you likely have gaps in your coverage, and it's very easy to write a whole lot of unit tests and then completely miss one namespace or one configuration or something, and then have it blow up. You can run all your tests, everything is green, and then you deploy to production, and then it breaks immediately. Like, I've done that too. So they both have merits, but they're both kind of missing something, and they're talking past each other. And it turns out there's a missing axis here, right? Because they treat this as a spectrum of you can either be fast and deterministic, but have gaps, or you can be slow and flaky and probably not have gaps. So on the bottom here, this bottom axis is test purity, and on the top is test size. So the test pyramid people are down to the right because they're using small deterministic tests, but they're also small. And then the end-to-end people are in the top left because they're using large, impure, flaky tests. But we can move to the top right, because remember in every chart, the good thing is in the top right. So we can have fast, deterministic tests that give us coverage of the entire system, right? And what would that look like? So it turns out it's already been done before. There's this great talk, Deterministic Simulation Testing of Distributed Systems. I was at Strange Loop about a decade ago. Highly recommend this talk. You should go watch it. But the Cliff's Notes are the speaker, Will Wilson. He was on the Foundation DB team. And they got started in the late 2000s. And at the time, there were horizontally scalable databases like Dynamo, which are fast and resilient to hardware failure, but they didn't have real transactions. And then there were single machine databases, like Postgres and whatever, where you have single writer, single hardware, and they're more or less correct, but they're not horizontally scalable, which has problems for both performance and resilience. And so Foundation said, we're going to go build a fast, correct distributed database. Now, because Dynamo already existed, they knew that they had to be correct, because if they were fast and distributed but not correct, then users could just go use Dynamo. So what they did was they built the thing using, they wrote their own dialect of C++, and they added actor-style concurrency. And then they took every single source of side effects and nondeterminism and put it behind an interface. And then they wrote test implementations for all of those. So you have the real implementation for reading and writing to disk, the real implementation for sending a network message, and then the test implementation is separate, pure code. And then in production, it runs on 3 or a dozen or 24 machines, and there are like 30 of these, however many actor processes that you need. But then when they're testing it, they run all of that in the same process. And then because they've controlled all sources of nondeterminism, and then they hook it up to quick check. And so then you get they'd run a test of okay, a user made this request, and then they would run all of the actors in the same process, and then ping pong the messages, and then it produces an output response. And then you can say, because they controlled even the thread scheduler, they would say, for all possible thread interleavings, assert that this input produces the same output. And once you've done that, you now have an in-memory, fast, deterministic test that gives you good confidence that you don't have race conditions. Right? This is incredibly powerful. And you can take it farther, because you have these test implementations, and so then you can say, let's simulate a failure of a third of the cluster hardware, or let's simulate the user makes a request, we read to disk, and then instead of giving them the actual data that they sent us in the previous request, we'll just silently flip some bits, and then let's prove that we still give the user a good response. So this is validating that they are correctly checking disks for corruption. So they're simulating hardware, disk failures. And they still had a physical hardware cluster, but this software-based approach was several orders of magnitude faster. And they eventually, I think they ended up discarding the hardware cluster, because the test cluster, they had like power supplies that they controlled over API, and like the power supplies started breaking. So like their test cluster broke, and the software did not. But because it was written software, it was orders of magnitude faster, and that gives them far more confidence that they were building a correct system. So what are the lessons learned from this? Isolate all of your sources of side effects and nondeterminism. Test the entire process in the same. Test the entire system in the same process. Hook it up to quick check, and as you see, there might be a flaw in this plan. So if you don't have a greenfield project, or if you don't want to work in C++, or you don't want to write your own programming language, what do we do? Well, we can incrementally approach the gains from this. So part 2, test.contract. So this started from a blog post. My journey on this started on a blog post that Nubank wrote, which is why we killed our end-to-end test suite. And it was a great post, and they talk about how they killed their end-to-end test suite using this new concept called contract testing. And I said, oh, that sounds great. I want to use that. But they didn't provide their source code. So I did. So this is my approach at the problem. And this is test.check applied to testing and mocking stateful protocols. So I'm going to show you a picture of your application, and mine. Everybody's app looks like this these days. It's a distributed system. You've got browsers, you've got API clients, you have your API, you've got a job queue, you've got a database. There's probably a reporting database. You got to send some emails. You're uploading, downloading files from S3, right? Like everybody's a distributed system. And setting this thing up is annoying, and getting a complete copy of production to every developer is usually cost infeasible. And then if you say, let's say all of engineering shares a cluster, or this team shares a cluster, and then you still have contention on that. So we were running test containers for a while to get the some Python AWS mock, and it was just a giant pain. I don't know if you've ever tried to run Linux x86 containers on an ARM Mac. Like, it's just annoying. So I wanted to get rid of this dependency. So we started with S3. And so you start with a normal Clojure protocol. In this case, we call it object storage. And you've got get object, put object, delete, list, very basic stuff. And you can start writing specs. What is the fdef spec for get object? It's like, well, it could return an input stream or nil, right? But that's not good enough for mocking, like completely removing this dependency from the rest of my test suite. Because if I do put object, get object, that should very definitely return the thing, unless there was like a delete in the middle or something like that. So you very quickly hit the point where you need to model state to have an effective copy of S3. So we define this model. Sorry, I don't expect you to read this whole thing. The point here is that this is a pure Clojure code. So if you imagine like you're going to write an in-memory toy example of S3, what would that look like? And that gives you a good intuition of what this is doing. So we have our protocol, and then we define this pure Clojure thing. So we say, for each protocol method, we're going to define a little, sorry, I don't have my mouse. You can't see my mouse over here. Oh yeah, okay, this works well enough. So we define this pure Clojure function that takes the state that the instance is currently in, and the arguments that, in this case, getObject was called with. And then we do some simple business logic, and so we say, so the state is just a normal Clojure map. And so we say, if that file is in the state map, then we're going to return this thing. And the thing that we're returning is a spec and a next state, and optionally a generator. And then if the key is not there, then we return a different spec. And so the whole idea here is that we normally treat specs as a static thing. You know, like the spec for a single function is always the same. But when you're modeling a stateful system, the spec, the way the thing should behave in the current state changes. So this is really just like a very small amount of state, and then you say, in this state, this method should return, if the key is there, it should return this thing, and if it's not there, it returns this thing. It's really just like specs on a finite state machine. Well, infinite state machine, but it's specs on a state machine. So this model describes the interactions between the methods, right? And then once you're there, you can do some cool things. So we have this function called verify. So you have the model, you have generators on the arguments, and you have specs on the return values. You have a real implementation of S3, and then because of Clojure 111, we can dynamically create new instances of a protocol method, or a protocol object. And so we can create a new instance of the protocol using the model. And then we have all the generators and the specs. So we can say, generate a sequence of calls, call the real thing, and call the model, get the specs off the model, and compare the real return values to the return values from the specs, and do they agree? And if they do, you now have confidence that the model is an accurate representation of the real thing. So then you run that in your test suite, and that's fine. But the real magic starts with the mocks. So now we have confidence that the model accurately describes the real thing. So you have this second function, mock, which takes the model and returns a new instance of the protocol. And now we can use that to decouple the real S3 from the rest of our test suite, right? So we've proven that the mock represents reality, and so we can just take that out, and so none of your other tests have to call real S3 anymore. So this decouples your test suite because you now have two pieces that can run independently, right? Because you can run verify either in CI or nightly, whatever you want. You can also run it like continuously, because that's now a test that you can run it continuously like in staging or production, because that's now a test that your upstream vendor has not changed their behavior. So the mock is great for CI. It also simplifies local development, right? Because now we don't need test containers anymore. And if you've ever worked in a big regulated industry where you have like, oh, you're not allowed to call that vendor from your laptop because IP whitelisting or whatever. Like you're only allowed to call it from the production cluster. Like developing on testing on that is always a pain. But now you have this mock, and we've proven using generative testing that the mock behaves like the real thing. So it's usually a pretty good substitute for development. And then another function we have is test proxy. So you can take the model, and you can take a real instance of the real S3 and return a new instance of the protocol that calls both of them. This gives you extra validation of the real world use. So GitHub has a great blog post about how they did this once. So they had their authentication and authorization service, and they wanted to rewrite it. And they wanted to rewrite it because the old one was gnarly and unreadable, but they also knew it was correct. So what they did was they deployed the old service, they wrote the new service, deployed old and new side by side in production, but only the old one is authoritative. So user A wants to visit page B, do we let them in, yes or no? But they called both of them, and so then they actually served the old response. But if the old and new response ever disagreed, they'd log an error. And so you deploy both of them, come back tomorrow, check the logs. Oh, okay, they disagree in these places, we have to go fix the bug, deploy it, and then let it run. And then once it runs for like a week without errors, you know that the new one is now handling all cases the same way the old one was. And then you can safely turn off the old one. So you can do that with test proxy, and it's also just useful to make sure that your call sequences in production are what you think they were in test, because they should never disagree in production, right? Final feature that we haven't done yet, but we could, this is like one PR away, is injecting errors. So you have what happens if 1% of the time when you call S3, instead of giving you the real result, it throws connection refused, or sleeps for 30 seconds and then gives you an answer, things like that. It's really simple once you've isolated things, because it's just a single middleware function. You might have noticed in the original, in the model slide, we have this return next state thing, and that looks a little unclojure-y because it's kind of like continuation passing style. But it turns out it's necessary for shrinking, and shrinking does work. When I was first hearing about test.check, people talked about how great shrinking was, and I was like, okay, it sounds like a nice to have, but I don't see the value. But then I wrote this, and it would generate like 50 commands and then blow up. I was like, okay, that's unreadable. So then I fixed shrinking, and then it shrunk that 50 command sequence down to 2. I was like, oh, okay, there's the bug. So because we're modeling a stateful system, and because we have shrinking, the model state must be a pure value, like not an atom wrapping a map, but like just a map. And the reason is because if we have this hypothetical call sequence where we do like create 1, create 2, delete 1, and that blows up, then quick check is going to shrink to like create 1, delete 1, and so that create 2 has to go away. But you can't undo state. So the easiest way is just at each step you hold on to the complete immutable value and then play forward. Yeah, so state has to be a pure value, and you have to continuation passing style it. So going back to our app, we've now exercised the impurity from S3, right? So we have verify running over on the side. All of our other tests are now using the pure mock. Local development has gotten simpler. And you can repeat this process. Like, you should understand all of the connections in your app, right? You should be able to know what they are, and you should be able to know what is going on that communication channel. And if you don't, you're going to have other correctness problems. So let's talk about some caveats and limitations. So first of all, test.contract is not a panacea. I'm not telling you to go replace any of your existing good testing strategies. I'd say this is in addition to your existing things. And I would use it only in, the whole goal of this is to test the interactions between the producers and consumers of a stateful protocol. So if you don't have state, just go use test.check. And the other goal here is you want to describe the requirements. So in your app, if you're calling S3 and you're not checking the return values, then like a valid spec for the return value is any, right? Because like you're not checking the return value, it doesn't matter what it was. So like start with the laziest possible model, and then add detail only as necessary. And the other thing is you're not trying to come up with a complete reproduction of S3. You're trying to define the minimum boundary, because like you could go go write thousands of lines to describe exactly how S3 works, but now you're coupled to S3, right? So the goal is that your goal probably should be, what is the lowest common denominator for object storage across all implementations? What are the bare requirements there, and only describe those. So I'm not telling you to go implement S3. So what are the lessons we can learn from like system design based on foundation and getting to these kind of pure system tests? This is going to sound insultingly obvious, but I promise most people don't do it most of the time, which is define the correctness for your system. People think, oh, I'm in this business, and so therefore like users want X. It's like, yeah, but like you need to turn that into a detailed requirement. What exactly are they sending you in the request. What exactly are you sending them in the response? What are you not accepting in the request? What are you promising is going to be in the response? Like, we should treat our programs as like pure functions in terms of, you give me this, I give you that. Like, I know it sounds like the most basic thing, but I promise most people don't do it most of the time. The other thing is you will not get a correct system from a complex system. Like, you must use simple components. So that means small pieces with very few moving parts and very clear lines of communication. You know, this piece accepts these kinds of inputs and only those, and then it only talks to this. So be wary of lots of moving parts, be wary of lots of responsibilities in the same component, and also be wary of like vague requirements. It should be very precise. So we've used test.contract. Defining the webhook API is easy. Defining the API for our product is easy. The job queue is easy. The email API is easy. There are two stragglers here that are not. Browsers they're a lost cause. Like, Chrome has no well-defined spec. It changes weekly, and describing Chrome is about as hard as implementing it, which is to say, all of us together are not going to do that. Databases, you have more of a fighting chance, though. So we want these deterministic system tests. So how do we, because we want to be able to prove that our system is actually correct under all conditions. So how do we get there? Like, what do we need out of our database? So if it has an in-memory configuration and it's pure, great, you're done. Just use that. If it has a simple interface, you can write a contract. And if it doesn't, like, you're in a world of pain. So, and by simple interface, I mean, like, the API is small, the API is simple, it's understandable. That's, I'm thinking things like RocksDB, FoundationDB. They're both key value databases with correct semantics. But like, most SQL databases are out, right? Does it sound fun to write the parser for SQL? No. Does it sound fun to write, the Postgres standard library with its like datetime parsing functions? No. Like, you don't want to write those. And what that means is that most SQL databases don't have a model of correctness that changes over time. The developers don't even agree what it's supposed to do, which I know sounds like a harsh claim, but you can go find the mailing lists. Like, we have the receipts. So, yeah, contracting a database, we need a simple API and little to no standard library. And then we also need a simple consistency model. And by consistency model, I mean this. So this is a great chart written by Kyle Kingsbury. Is Kyle here? No, I guess not. Well, I'll try not to mangle his work. But so Kyle breaks distributed databases, like, for fun, I guess. And vendors would write silly things on their websites, like this database is both available and consistent because network partitions never happen. Or, this database is transactional and multi-master and will survive, 2 out of 3 node hardware failures without losing writes. And Kyle said, those sound like testable hypotheses. I can build a test cluster and run, test exactly that and turn up lots of bugs. So that's one reason to be skeptical of database vendors. But the other is the consistency problem. So the one at the top here is strict serializable. I'll try not to mangle this. So if you have a concurrent system with concurrent readers, concurrent writers, and real transactions, then if one user starts a transaction, does some reads, does some writes, and commits, what they will see will be as if they were the only writer on the system. And that's great. That's incredibly powerful because, like, all concurrency problems basically just go away. And then Everything else on this chart below strict serializable is another word for bug, right? Like programmers have 50 words for bug, distributed systems researchers have 50 words for race condition, which is also another word for bug. But then if we're trying to write these deterministic system tests on top of that, the problem gets even worse, because you write the contract for like the single-threaded behavior, and like, okay, we've correctly modeled all of that, and now you have to handle concurrency. And you have to say, okay, if there are concurrent writers, then some of the time when I do this transaction, I will see stale data. And like, you have to write the code to show that that happens. And then like verifying that is a giant pain. Like if you ever read the Jepsen posts, it's quite obvious these take a lot of work. And that's to find like one bug, and then if you find it, how do you know that it's gone, right? And so then assume for a second you actually do model that. Now you have modeled incidental complexity, and you're forcing your downstream consumers to handle it. So now your downstream tests get even more complex. So the way to avoid all of that is just pick a database at the top. To get something strict serializable and sleep better at night. So, in summary, isolate all sources of side effects and nondeterminism. Test the entire system in a single process. Quick check all the things. Use simple components, and so that's both depend on simple components and produce simple components. And then be explicit about your guarantees. Again, up and down. Like, I depend on this, and like if this doesn't hold, then the rest of my system has a problem. And then be explicit about what you're promising. I promise that my API is strict serializable. And then test those guarantees in both directions. So, thanks.